Now what we're going to do is we are going to take a very basic and brief introduction into one of my most favorite topics in mathematics, and that is the world of trigonometry. We'll be starting with our right triangle trigonometry. Now, hopefully you all are familiar, at least to some degree, the Pythagorean theorem, which is the lovely right triangle formula that allows us to calculate a missing side of a right triangle given two other sides of said triangle. And it states that the square of the hypotenuse is equivalent to the sum of the squares of the legs, with the hypotenuse being the longest side of the triangle. And if we don't even know the sides of the triangle, the lengths of them, by looking at the diagram we can identify which side is C because C is always opposite the right angle. Now, which side is A and which side is B doesn't really matter, so we could switch these and we'll still get the same result because addition is commutative. And so this formula is very well known and one of the earliest concepts taught within geometry and trigonometry. And so we'll go through a couple basic examples of using the Pythagorean theorem. If we want to find the length of side BC, well, we know that it is our hypotenuse because it is opposite of angle A, which is our right angle here. So we know that A and B are both going to be either 4 or 6. And again, we could switch those. A could be 6 and B could be 4. But most importantly, we know that using our formula of A squared plus B squared equals C squared, we can substitute these values in for the legs, and then we can go ahead and calculate the value of C. As we square the numbers and add them, we get C squared equals 52. And in order to finish our solution, we have to go ahead and square root 52. Now here's where we could have two different types of answers. We could either have an approximate or we could have an exact solution. And we need to simplify based on the scenario and whatever the directions are calling for. If we wanted an approximate answer, well, we could go ahead and round the square root of 52 to be approximately 7.2. If we were rounding to one decimal place. However, if we want an exact solution, then we have to simplify the square root of 52. So again, we have to think about how we can separate the square root of 52 into a factor that we can get an integer root from. And so if we rewrite this as the square root of 4 times 13, 4 is a perfect square, 4 times 13 gives me 52. This allows me to take the square root of 4 and leave the radical 13. So we could have a rounded answer or we could have an exact answer depending on what the situation requires. Now for our next triangle, I want you to think for a second and try to identify what our hypotenuse of this triangle is going to be. Is the hypotenuse going to be side EF? Is the hypotenuse going to be side DF? Or is the hypotenuse going to be side DE? And how do you know? Well, opposite our right angle is side DE, which means that our hypotenuse is 25. So A squared plus B squared equals C squared. We can use 24 for either A or B. And B is the value we'll be solving this time. We go ahead and square our values. Isolate B squared, and then we square root, and we get a length of 7. Now this one ended up with much nicer numbers, and we noticed that the lengths of sides A, B, and C were all integer values, and this gives us what we call Pythagorean triples. Pythagorean triples are special combinations of integers that satisfy the Pythagorean theorem. One of the most common Pythagorean triples is a 3, 4, 5 right triangle, where the legs are lengths 3 and 4, and 5 is the hypotenuse. And we can see that 3 squared plus 4 squared does indeed equal 5 squared, showing that they satisfy the Pythagorean theorem. Now, the nice thing about Pythagorean triples is that if we know one, we actually know a bunch of others, because any multiples of these numbers are also Pythagorean triples. So if I take a 3, 4, 5 triangle, and I double all the side lengths, I get a 6, 8, 12 triangle. Or if I triple all the side lengths, I have 9, 12, 15. If I multiply all the side lengths by 10, I get a 30, 40, 50 right triangle, all of these are Pythagorean triples. They satisfy the Pythagorean theorem. Along with 3, 4, 5, two other really common triples include the 5, 12, 13, and the 7, 24, 25. And again, just like with the 3, 4, 5, we could scale these up. And if I were to double all the side lengths, I have now created a new Pythagorean triple. And as far as the SAT is concerned, knowing these Pythagorean triples can be really beneficial because when we're having questions that involve the Pythagorean theorem, a lot of times they'll utilize the triples for two reasons. One, all the side lengths are nice, easy integers that allow us to work out to much simpler numbers without having to do some tedious simplifying. But it also allows us to speed up the process of applying the Pythagorean theorem and still allow for time to use and solve for more complex problems. And so here we have a problem that involves similar triangles like we saw with this previous lesson, where we want to calculate a missing side length. We want to find the length of side AC, which is the hypotenuse of the larger triangle of these two similar triangles that are presented. And so we could use a previous method of finding the proportional relationship. They tell us the length of CD over here is 6, and we could set up a proportional relationship where we know that we could use our Pythagorean theorem to find this missing side and set up a proportion with x and 6 and 5 and be able to find all the side lengths. But by knowing the Pythagorean triple, it saves us a lot of time by thinking about the similar triangles and those multiples of the triangles as well. So I noticed that my hypotenuse here is a length of 5, and one of my legs is 4, satisfying two of the three requirements for a Pythagorean triple, 3, 4, 5. And so just by noticing that and recognizing that triple, I know that this has to be a side length of 3. And since these are similar triangles, the side lengths have to be proportional, which means that our triangle with side length CD is twice as large as our smaller triangle. So that means all the sides are scaled up by 2. That means our 3, 4, 5 triangle, everything is scaled up by a factor of 2, which means our larger triangle is a 6, 8, 10 triangle. And since it's a 6, 8, 10 triangle, and we know this side is a side 6, our other leg has to be side length of 8, and our hypotenuse is a side length of 10, giving us the solution that AC equals 10. So recognizing these triples allows us to quickly and efficiently compare similar triangles that follow the same pattern.